Record. So we did get through a lot of talk about temperature and how temperature is kinetic energy. It's a measure of kinetic energy. We talked about how low it can go to absolute zero, at 0 degrees Kelvin or negative 273 Celsius is the absolute lowest you can go. And we left off talking about thermal energy. So let's pose this little slide to us. Say you have a sparkler. Now there's a reason why you can get hit by the sparks, but you don't get burned. In terms of thermal energy, what do you guys suppose that is? Guys, the sparks are 2,000 degrees Celsius. Anton, what do you think?
They're so small that they're surfacing this space.
I would say you're right on the money. The energy is being flowing or transferring. Thermal energy has a lot of energy for every little molecule. But there's, relatively speaking, compared to the air around it, there's very few molecules for each spark. So you get a very low transfer of energy. So if kinetic energy is equated with thermal energy in terms of a molecular level, this is submicroscopic, you get a lot of collisions. Okay, imagine you're playing the lottery. You ever see them have the machine on TV with the lottery? You have all these numbers on the balls and they're bouncing around everywhere. That's kind of the way the kinetic energy transfers, through collisions. So then what is heat? Well, heat is because of all these collisions occurring, we get a flow of thermal energy. The flow of thermal energy is due to a difference in temperature. So heat is the flow or the transit of thermal energy due to a temperature difference. Always, 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 heat is going to flow from high to low, hot to cold. It's a natural tendency of heat to flow from hot to cold. Even if you put ice in your drink, you're not putting cold in the drink. You're taking the heat and moving it to the ice. So whatever temperature your drink is, it's going to level out and form a sort of a thermal equilibrium with the ice. Even if you turn your air conditioner on, you're pumping heat out. The same with your refrigerator. Those are heat pumps. Your refrigerator and freezer have to move the heat out of the system because the natural tendency is to go from hot to cold. Is that right? Is that right? Let's compare two different sizes of water being heated up by the same amount of heat. So on the left is 1 liter of water, and on the right is 3 liters of water. Both of these pots absorb the same quantity or amount of heat. So they're on the stove and they have the same burner, same temperature, right? But the temperature inside of this pot on the left is going to increase 3 times as much as the one on the right. Why? Because, thank you, because there's 3 times as much water on the one in the right. So you have less volume of water on the left, less amount of molecules, right? Less mass of water. So it's going to have the same amount of collisions, but less amount of matter or mass. The one on the right has more matter, so the collisions are dissipated more. It takes, obviously it takes more time for you guys to boil a big pot of water than it takes to boil a small pot of water. So let's check. The question says, when the same amount of heat is added to each of the 2 containers of water, The temperature increase in each will be A, B, C, or D. Nick. Well, they have different amounts of water. So you think they're going to increase by the same temperature? Like one's a small pot of water and one's a big pot of water. You want to think about that again? B, I would agree 100% with you on that one. It really depends on how much water is in the pot, right? If you have a small pot of water, it's going to take less time to boil than a big pot of water. You have less amount of water to collide and cause these kinetic energies to be transferred. So remember, heat is how much kinetic energy is in the system. So if you're playing the lotto and you have like the same amount of chances as far as like the balls go, you're going to get the same, you know, energy bouncing in there. But if you have a container that has less balls in there, they're going to bounce around faster. They're going to have more collisions. If you have the ball shaker with more balls in there, you could have a lot of collisions, but they're not as powerful, I should say, or not as bouncy. Think about that for a minute while we talk about quantities of heat. What we just described was the quality of heat in words, right? Qualitative. Quantitative is mathematical speaking. So heat, if it's energy in transit or energy that's flowing, it's measured in units of energy. We use joules to measure energy in the previous unit. So how can I relate joules to a quantity of heat? Right? So heat energy is in transit. What else is in transit, guys? The bus, the train, the Uber. We talk about transit. We're talking about things moving. So heat is energy that's moving. And if we're going to take the unit for energy as joules, we want to relate it to something that we can measure like in the lab in everyday life. So this is where we come up with the calorie. The calorie, lowercase c. The calorie is defined as the amount of heat that is needed to raise the temperature of 1 gram of water by 1 degree Celsius. And let me show you what 1 gram of water looks like. It's equal to a milliliter. So I can take this graduated cylinder and show you what 1 milliliter of water looks like, and it's up to this blue line. That's not a lot. So it's going to take you 4.19 joules of energy to heat this much water by 1 degree Celsius. That's not a lot, is it? No, that's nothing. Right? I mean, oh, okay. You barely feel it.
Wait till I'm there.
Just a millimeter. I bless you, Anton.
Oh, it's sink water?
So a calorie is 4.19 joules of energy used to raise a gram of water by 1 degree Celsius. On my food label, I don't know. What do you guys eat? Flaming Hots? What chips do you guys eat? Doritos, 3D or 2D? Do you eat 3D Doritos or 2D Doritos? No, there's a new one called 3D.
The normal kind.
Yeah,
The triangles. Or Kate, she has bugles. Kate, do you ever put them on your fingers and like do a little hat dance with them? Oh, that's just a bugles. Am I the only one that does the little put the bugles on your finger thing? Not gonna lie, love them. But on the back of my bugle bag, it's going to give me a measurement called calories. But this is actually the measurement of energy that's released when my body metabolizes the bugle. And the bugle measurement on the bag is literally kilocalories. So 1,000 calories is 1 kilocalorie. On the bag, it's capital C. In the lab, it's lowercase c. So in the science class, we're going to say lowercase c for calorie, but on your food labels, it's going to say uppercase C, capital C. The capital C is equal to 1 kilocalorie. So that's one difference that you're going to notice. A kilocalorie, or a capital C, is the heat needed to change the temperature of 1 kilogram of water by 1 degree Celsius. Do you guys need me to show you what a kilogram of water looks like?
Sure.
You sure about that? It should be about a liter. Okay.
Show me a liter of water.
So the summary of what we just learned is that A, heat is energy that's moving or in transit. B, we measure heat as the energy in joules, calories, or kilocalories, capital C. And that 1 food calorie, the kilocalorie, is equal to 1,000 calories. This man's going to eat 1 peanut and the label says that it's 10 calories. But to the scientist, the peanut is 10,000 calories because that's lowercase c. The 1 peanut has 41,900 joules of energy when it's digested. And that wraps it up. We are not going to cover thermodynamics laws, and I'm going to post these notes. Here's what we're going to be responsible for. Oh, don't look at that. We're going to be responsible for these assignments. If you go into our Google Classroom, on the classwork tab, over the last couple of days, here's what we've had. On the 9th, this was due for at-home students. This was a review of momentum and impulse. 3 of the people in the class need to get that turned in. Chauncey, Kate, and Dave. Okay? I don't know how that happened. Yesterday. This was due yesterday at midnight. 5 people have not turned it in yet. So Jeffrey, Darius, Xander, Anton, Kate. This is page 424 in the textbook, number 1 through 5. I want to upload the answers tomorrow, so I need you guys to do it before that. And the heat vocab, you had 11 words. 7 are assigned, seniors. This is not looking good for us.
I didn't do it. I'll do it when I get.
All right. Here's the deal, kids. I can do async if you do the work, but if you don't do the work, I can't do async. All right. I honestly can't risk it. I need to trust you that you're going to do your assignments. Okay. So that is due tonight at midnight. Those vocab words. Find those in chapter 21, 22, and 24. That's what our whole unit covers. Okay. All right.